Good afternoon. Can you hear me? Okay. Good afternoon. This is the collaborative annual lecture between Wanger and C2ST, plus the Department of the Chemical, Mechanical Aerospace, Electrical, and Civil and Environmental Engineering. This is a forum that brings us all together. And it's my pleasure to introduce you our distinguished lecturer this time, Professor Rakesh Agrawal, which is currently Winthrop Stone Distinguished Professor of Chemical Engineering at Purdue University. He joined Purdue about year 2004. Prior to that, he was in Air Product and Chemicals, Inc. between 1980 and 2004. Rakesh received his Bachelor of Technology in Chemical Engineering from IIT, not this one, IIT Kanpur, Master of Chemical Engineering, University of Delaware, and a doctorate in Chemical Engineering from MIT. Professor Agrawal, interest is very broad. Recent interest is in energy production issues, especially from renewable energy sources, such as solar, and the thrust of the research is to fabricate low-cost solar cell based on nanotechnology. Another major thrust of his current research is development of optimization of the processes to meet the needs, including transportation, fuel, chemicals, electricity, and primarily from renewable energy sources to enable them to make it more sustainable. His effort also focused on efficient conversion of biomass to liquid fuel. Professor Agrawal received several national and international awards. I can't list everything, otherwise he would not have a time to give his lecture. I want to mention a few. One being recipient of National Medal of Technology and Innovation in 2011 from President of the United States. This is basically, if you are not familiar with that, is the highest honor given by US government for technology and innovation. He is a member of US National Academy of Engineering, fellow of American Academy of Art and Science, US National Academy of Inventors, American Institute of Chemical Engineers, and Indian National Academy of Engineering. On top of everything else, he received the Excellence in Teaching Chemical Engineering Award from Purdue University. He is also recipient of AICHE Excellence in Industrial Gas Technology Award, Chemical Engineering Practice Award, and Fuel and Chemical Division Awards. He's also presented 2005 American Institute of Chemical Engineering Institute lecture. It's a great honor and pleasure for me to introduce Professor Agrawal to you.
Thank you, Hamid. It's truly a pleasure and an honor to be here, and I'm absolutely delighted to be here to give this talk. And the primary goal of today's presentation is, as you heard from Hamid, I worked in industry most of my life, and so when I moved to Purdue in 2004, suddenly Purdue had given me a seed grant, and I had a clean sheet of paper to start from. And so what I will do today is probably take you through the same journey which I took since 2004. This entirely done at Purdue University, actually. And basically the way it evolved was that my wife and I were traveling we lived in Allentown, Pennsylvania, and we were traveling to Purdue. We packed everything in our van, and we were driving across the Pennsylvania Turnpike. And she asked me, "What are you going to do now?" And I looked at her. That's a good question. What am I going to do now? Right? And so the part of that, so wanted to do something new, and so I will take you through that journey, actually. And that was during that 10-hour journey, ideas germinated what I want to do, and that's exactly what I will describe you. Okay, so what it is like, if you look at the human race, like, how we have lived, and this is what I did in my own mind actually that time. Like, for most of its existence, human population has been fairly low, like, and all this time, the human population have lived for its energy from biomass, cut the trees, collect it. People would go in the forests, chop it out, bring it home. A lot of human time was spent in just collecting, okay, and then burning and storing and so forth, okay. But then something happened. Something happened around 1700 something, and there was a remarkable change in the human civilization actually. And I'm sure, like, all of you know what that was. That was the steam engine, right? So once the steam engine came, industrial era began, okay, and the ability of the human race, the first time the steam engines, the first use they were put to was to pump out of the coal mine so more coal could be mined out, okay? So the ability to take that coal, that high energy density material in buckets, okay, changed us forever, okay? And having that high energy density fuel, like, as against going and collecting fuel, like, and then came along the production of ammonia, okay, from air, and that two events, okay, and the human population has been on a rise since then. Like, there is no shortage of food. Ammonia, you can make fertilizers, urea, and so forth. And so this is an era of fossils, right? So we, human race, have a lot to thank to the fossil fuels, okay? Even the laws of thermodynamics, as we know today, came out of the fossils, right? Because when the steam engines came along, like, so what happened that time, okay, like Hamid's steam engine was better than mine, and where is Murad? Okay, with power, all his power electronics, his steam engine was better than, than someone else's, okay? And young man Carnot asked, is that really true? Like, can you just keep making things more and more and more efficient, okay? And in trying to answer that very basic question, right, okay, he came up with all the concepts, a genius, right, transferring reversibly the heat from a high temperature to a low temperature and coming up with the laws of thermodynamics, okay? So fossils really have changed us forever. And also the sheer fact that I'm here giving you the lecture is also because of the fossils, okay? Because otherwise I would not be here, okay? There's no way to travel across from the part of the world where I was born to travel and come and give. So the fossils have played a great role. We have a lot to thank to the fossils, okay? But the question is, okay, the question in front of us is, okay, there's a limited supply of fossils, okay? The rate at which we consume, okay, is far bigger than the rate at which it is formed, okay? And also the environmental consequences which accompany that, okay? So we have to make a transition, okay? And the question is, when are we going to make that transition, okay? And so when I made these slides, I asked my graduate student to draw this around 2100 or something, or 2050, but he drew it at 22. He's a young person, he is more optimistic, he thinks fossil is going to last long, so he drew, and I looked at it, I said, boy, you know what? I did not ask you to draw it at 2200, but it doesn't matter, okay? You pick your year, okay? You pick your year, you pick your time frame, okay? The point is that we have to make that transition, and I happen to believe, and that was that Pennsylvania Turnpike journey which I was telling you earlier. We have to make that transition, okay? And once we make that transition, we have to prepare for it today, okay? So that's the thing. So why solar energy, okay? So why do I think, by the way, wind is part of it, even though I will not be talking about wind at all, okay? But because I don't do research in wind, but so wind is also part of solar in some manner, okay? Wind flows. But if you look at the solar energy, the consumption, like, the amount which falls on Earth is far more, orders of magnitude more than what we, as a human race, what we consume in a year, okay? But most of the solar energy which falls on Earth does not stay on Earth, right? Because Earth immediately radiates it back to the outer space, which is at 2.73 degrees Kelvin. And thanks that it doesn't stay on Earth. Otherwise, Earth would be a hot place to live, right? So the most of it comes, almost all of it comes in leaves, okay? Some of it get trapped, like in terms of clouds, trees grow, and so forth, but majority of the energy leaves. So the energy which comes is the most abundant source, and if we learned how to do solar, it can very easily meet all the needs we have, okay? It could supply us everything what we need. So, but then if it is so obvious that it is so much of it, then, and what I would like to do today is, and this is exactly what I had in mind that particular day I described to you, is that if I were to get up 100 or 200 years from now, suddenly, if I were to come to this planet Earth, I know that I won't, but suppose if I did randomly, okay? And if I had to make from my cup of tea to my food, my fertilizers, my clothes, my transport, everything came from solar photons, okay? How would that world be? Okay. What would it look like? Okay. So it is water purification is not shown on here. Water purification is part of that. Everything, whatever. So imagine a world which is driven by solar photons, and what would that be? Okay. And that's the research which I started. Okay. And that's what. So this slide more or less sums up what I envision. Okay. So if that is the case, if the solar energy is so much in excess, so why its use is not prevalent? Why aren't we using it? Okay, so what's the next question I asked myself? Okay, so and the reasons are some of these reasons which I try to understand for myself why we are not using it. Some of the basic reasons are like this. So all of us more or less drive our cars. We fill the gasoline. So if you fill the gas in the car, you're filling. U.S. law requires that each pump stations pump gas at the rate of 10 gallons a minute. So that's the rate at which you are pumping. And then what you'll do is you find out that's roughly 20 megawatts of power which you are putting in your car when you're filling that gasoline. Okay, so the question is, if I needed the same rate, if I needed the power from sun, okay, what will it take? Okay, so if you look at the solar, a typical solar radiation is of the order of 1,000 watts per meter square. Okay, so to get 20 megawatts of power supply, you need 20,000 meters square. So if I were to recover solar energy with 100% efficiency, okay, I will need 3 soccer fields or 4 football fields, okay, all of that covered to get with the same rate at which I'm filling my gasoline. Yep. I'm an engineer. I know there's no such thing as 100% efficiency. Okay, if I were to recover it, with 20% efficiency, let us say for the sake of discussion, okay, there'll be 20 football fields, okay, giving me what I just filled in my tank in my car, okay, in that period of 1 minute, okay. So that tells us, what is it telling us? It is telling us that the solar energy, okay, is very, very dilute, okay. And you know what? As an engineer, that's a bad news for me because my energy source is very dilute, okay. But as a human race, that's a great thing, right? It is dilute, otherwise we would be burnt. We would not be here. We would not be even talking to each other, yeah. So what's great as a human being is really a bad news as an engineer because my source is very dilute. That means I need to get large areas to be covered. Okay, and worse is not only that I need to cover large areas, even just for that, what I showed you, a gallon, that power I was consuming, but the amount I need, right? So if I look at the amount I need, like in US, for example, in a year we consume 97.3 quarts, okay? And for the graduate students in the audience, like if you're like me, when I asked my graduate student, he came and told me it is Professor Earl, that time it was close to 100 quarts back in 2004, 2005. Our energy consumption has been going down, by the way. Okay, so it is like 100 quarts. He told me, I looked at him, I said, 100 quarts, what is 100 quarts, right? Okay, I have no feel for it, what 100 quarts means, right? So we looked at each other, and then what we did was he said, okay, all right, if I take these many trillion liters of gasoline, roughly close to 3 trillion gasoline, like it will has the same energy as 100 quarts of energy. Okay, so we know. So I looked at him. I said, 3 trillion liters of gasoline. I still can't relate to it. It's too big a number for me. Okay, and then what I did was I divided that by 365 days. Okay, 300 million people. Okay, then I know per day per person how much is that, and that's close to 7 liters, okay, and so, sorry, 7 gallons, okay, so it's close to 7 gallons, and I wonder how many of you in the audience even drink 7 gallons of water per day, yeah? It's a sobering thought, okay, like, let alone 7 gallons of milk, we don't even drink 7 gallons of water per day, but each one of you, including myself here, each one of us, okay, consume every day, on an average in this nation, okay, 7 gallons of gasoline, okay? So what is it telling me? Okay, I'm sitting in my office, I'm looking out of the window. What it is telling me is not only this energy, solar energy is very dilute, but I need a lot of it. Okay, all right, so and large areas need to be covered. Okay, so energy, so the low density solar energy is really a challenge. Okay, and if you want to replace a large scale is only possible if it is cost effective. So what it means is, if I'm going to use it, it has to be very low cost. And that time people would tell me that, don't worry, even if it is 10% efficient, that's good enough. It's not. The difference between 10% and 20% is half the land area. Okay? And just the mere act of going, the example I told you about 20 football fields, just the mere act of going, buying just cheap cloth and covering that that area itself is daunting. Okay? So it will still be a cost. So what we are learning here is it has to be efficient, okay, and it has to be low cost. Okay? All right? And so the harnessing efficiency, so it has to be low cost with higher efficiencies, not low cost with low efficiencies, okay? And of course, its use is intermittent. Solar energy is not there all the time. So what that means is, as an engineer, that's even a worse news for me, because as a chemical engineer, when I build a plant, right? When I build a plant and I go and I borrow a loan from a bank, that plant is producing 24 hours, right? Okay. And since it is producing 24 hours, okay, at least I can pay my loan back and I can pay the interest on a 24-hour basis. But if I build a solar power plant, okay, a bank is going to charge me on a 24-hour basis their interest, okay. But this thing produces only 5 hours a day on an average, okay. It sits idle, okay. So not only it has to be low cost, it has to be low cost by a factor of 5 again, okay. So suddenly you realize how difficult this task is, okay. And that's why the use is not prevalent, okay. So I basically concluded, okay, all right, so now we need to do research which has to be, very low cost, high efficiency, and so forth and so forth, okay. So the other thing which I learned very quickly at that point in time, that the solar economy, if I wanted to make it happen, I have to look, there are too many legs and arms of this system, okay. We have to look at the entire system together. We can't look at one versus the other. And I will explain to you as I move forward, as I understood it slowly with time. Okay, so energy systems engineering, when we talk about solar energy, we have to worry about all the aspects. Harvesting it, capturing, transforming it, converting it, storing it, distributing it, using it, okay? And after using, because the first law tells us energy is conserved, there's nothing about energy being, after I've used it, I have to discard it. It has to go back in the outer space, okay, because energy just keeps moving, okay. So I have to take the entire system, and I have to learn the entire system in its totality, okay. So what does that mean, okay? And I will give you 2 examples, okay, from my own research on this, okay. And why it is essential, because what I found out early on, that a lot of research I was doing, I was landing into wrong conclusions, okay, because I was looking only bits and pieces rather than the entire system, okay. So what do I mean by that? So for example, one of the research, because I'm on Purdue University campus, and as you know, Purdue is a big agricultural university, and being a big agricultural university, there are a lot of researchers who are biological bent, and they produce liquid fuel. So there's a big buzz, corn to methanol, corn to ethanol, corn to butanol. Like there was a lot of research being done, and there was a big emphasis on that. And is that the correct thing to do? Okay, and I begin to ask those questions. So one of my graduate students, the very first graduate student, Navneet Singh, what he did was he took the biomass, and I'm showing SA biomass. SA biomass is sustainably available waste biomass, meaning a biomass which you get from existing agricultural and forestry practices. And what that means is once you grow corn, you collect your corn kernels, and then whatever is left, you can collect 1/3 of the plant without causing an imbalanced carbon balance in the soil. You can collect 1/3 of the corn, okay? And that would be SA biomass, meaning no additional land, no additional fertilizer, no water, nothing, okay? So you can collect that, and what he was looking for, taking biomass and converting it to liquid fuel using different processes. Pick your favorite process, whether gasification, fermentation, pyrolysis, whatever you want, okay? And what we found very quickly, that no matter which process we picked, when we modeled it, we found that 40% of the carbon in the biomass would be recovered as liquid fuel, okay? So we said, okay, so it doesn't matter. So people had their own favorite processes, which they told was better than yours, but all of them were roughly 40% carbon recovery. Once we learned that, we look at roughly 500 million tons per year of sustainable biomass in US. In 2015, the transportation fuel uses roughly 13.6 million barrels. And if you took all that conversion, you find that you make somewhere around 2 million barrels per day. So if I took all the SA biomass, which is 500 million tons a year, you could make roughly 15-20% of the US oil need, okay? But you still need more than that. It's only a small fraction. So how get the more liquid, okay? So the question was, at that point in time, we Nonit and I looked at each other. What should we do now? We need more fuel. Should we grow more biomass? Okay, and if you want to grow more biomass, right, you need additional land. Okay, you need to do something. Okay, and if you're going to use additional land, the issue is not very trivial anymore. Okay, so what we did was, actually rather what he did was, okay, we looked into, if I have a solar photons from a given land area, and if I'm recovering it as energy, okay, what are the various efficiencies at which we can recover? Remember, I told you earlier, efficiency is very important. Okay, it's not something to be ignored. So if I recover solar photons as heat, I can get 1,000, 1,200 degrees Celsius level heat, very high exergy heat with roughly 70% efficiency with the black body absorbers. Okay, electricity you can go and buy today, 18, 15, 18% efficient photovoltaics, right? And of course, the hydrogen is the same thing. Even if you were to use electricity and use an electrolyzer, half the efficiency, but still you are there. You have pretty high efficiency. But look at the biomass. If I go and grow biomass on the given land, okay, a typical efficiency in the United States is close to 1%. Okay, there's a big difference between 1% and 20% or 70%. Okay, and on top of that, if I take that biomass and convert it to liquid fuel, okay, again, I know as a chemical engineer, I have to take another hit of 50 to 75% of that. Okay, so in the end, what I'll end up with is a very small energy recovery from the atmosphere. Okay, so the issue is at this point in time, if you want more additional liquid fuel, should you be growing more biomass? And the answer is no. Okay, because it's such a low energy recovery. It doesn't matter whether you're growing LG or you're growing LG is 5% or something. Okay, it doesn't matter. It's very low efficiency. So we made an observation at that point in time, and I still believe that biomass is primarily a carbon source and is not an energy source. Okay, so if as a chemical engineer, if I have to grow, and what Hamid was telling me yesterday, and again this morning in our conversations, okay, and I totally believe him, is the CO2 concentration in the atmosphere is getting higher and higher. And we have all this hotness in the environment, right? Like, rains and things are. And this morning, like, when I was told by Muhammad that we have these hurricanes in islands much earlier because of all this CO2. And when I started my career as a young engineer, the amount of CO2, I used to design plants for 250 parts per million CO2. The first air separation plants I designed by my own hand, we designed for 250 parts per million CO2. And now the CO2 is 405, 410 parts per million, right? So it's a very high concentration of CO2. But as an engineer, if I have to go and recover that CO2 from the atmosphere, okay, it's a very inefficient process, right? Imagine, if you may, like, I have a beaker here and I have a forceps, and the million molecules are going by me, right? And all the molecules, pick a color, are green in color, except 405 molecules, which are black in color. And my job is to catch those 405 and put it in the beaker. Yeah? Would you like to do that job? Absolutely not. Okay? Entropically, very unfavorable process. Okay? That's the point I want to bring. So on one hand, we see that the concentration is going high so much, and we complain about the warming, global warming, and so forth. And yet, as an engineer, if I have to capture that CO2, it's a very inefficient, undoable process. But yet, Mother Nature has done exactly the same thing, right? All those leaves, when the molecules are impinging on it, it captured those few parts per million carbon dioxide atoms, and gave us this dense form of carbon, which some people are holding in the hand, right? And yet, when we are recovering, making liquid fuel, we are discarding 60% of that carbon back to the atmosphere. And then now we are searching for growing more biomass. Okay, it doesn't jive together. Okay, so a better process would be is to take heat, electricity, and hydrogen, which are recovered in much higher efficiencies. Okay, with a much lower land area. Okay, and go after those 60% carbon, 60 carbon atoms, which are going to the atmosphere as CO2, okay, and not let that happen. Store this energy on the back of that carbon. So by the way, why is that 60% carbon goes to the atmosphere as CO2? The reason is biomass, okay, is partially oxidized, right, 35% oxygen. So per carbon atom, biomass has lower energy than per carbon atom gasoline would have. Okay, because gasoline has no oxygen on it. So what happens is you take 3 carbon atoms of biomass, they will have the same energy as 2 carbon atoms in gasoline. Okay, so immediately tells us, there's no way first law tells us we can't take this 3 carbon atoms of biomass and get 3 carbon atoms of high energy gasoline unless until we put additional source of energy. And on top of that, the inefficiencies which come along with it. So we need to think of new processes. The point is we need to think of new processes, and this is what we learned early on from our modeling, okay, that we need to take other energies. And by the way, I really don't have a good answer what economical process you would design. Okay, now that's the creativity and ingenuity which is needed. Okay, of course I have a lot of processes which could, but I don't have the one which is economical. Let's put it this way. Okay, for example, in my group, then we started a research, like we built a fast hydropyrolysis unit with the biomass, where we hydrodeoxygenate the biomass and directly make the liquid. And we demonstrated that. We built a reactor which runs at 50 atmospheres and so forth and so forth. So we finally demonstrated that, but that's not the goal of today's talk. But that could be another separate talk on itself. But I collaborated, but it came out of my research in the energy systems modeling. The message I was trying to give here is I used the systems modeling to come up with what to do research in terms of the real life research. Okay, so if you look at now SA biomass, and if you take all the 100% biomass as carbon, because you're using additional sources now, which are at higher efficiencies, what you find is you can make 6 million barrels a day of US oil need. That's 43%. That has improved, right? Okay, but still, we are short of nearly half of the liquid fuel you would need. Okay, so what should we do now? So when my guys student was sitting with me, and we were both looking at each other, and then we learned, okay, we need additional liquid fuel. Okay, the point is we were asking wrong questions all this time, right? Okay, we were asking question of how to make oil from biomass or from solar. But why do you need the oil? And that's what I mean by energy systems engineering. Okay. Actual need is the transportation. We should have been asking a question, how do we use solar energy for transportation? Not the question we were asking. Okay. So what happens is you ask a wrong question and you spend next 3 years doing a wrong research. Yeah, right? Okay. The question we should have been asking is, okay, so here is the solar energy, and our interest is transportation, and our interest in transportation is all kind of transportations, me going from home to the department, right? Then I'm on sabbatical this semester on Denver, and when Hamid is calling me from Denver to Chicago, okay, that's another distance. And when I go to India from Chicago or from Newark all the way to New Delhi, that's another distance, and we need to understand all that, okay? So it is a very different question, and once you begin to ask that question, then you realize who cares what liquid fuel we have and how much we have, but as long as the entire system, whether it is hydrogen for fuel cells, in electric-driven vehicles, power, you have to optimize the entire system. The point I was trying to tell you is one has to look at the entire system to understand. Okay? And that's why the energy systems engineering is important. So you don't end up using corn kernels to make gasoline while you should be using that for food, okay? And so forth. Okay? So it's important. Okay? So it's very important to ask right questions, do a right analysis, otherwise, and I will give you another example. I will give you 2 examples quick, and then so there's a notion here, and I started my talk also by telling you earlier, there's a lot of solar energy. Don't worry, if you can meet the entire human need, and that's what I believed for 10, 11 years, till one day, okay? So if you look at all the solar farms in the world, meaning photovoltaic farms, okay? So there are a lot of photovoltaic farms now built in the world, okay, in different parts of the world, from anywhere from Japan, US, UK is, you can see, and you can look at how much power they are producing based on 24-hour average, okay? So what you see insolation, some of you think of 1,000 watts per meter square, but it is only 220 because it is based on 24-hour average, not what is falling, because we human race live on a 24-hour basis, so it is 1/5 of 1,000, okay, roughly, okay? And then you look at the same thing about the power. What you find is that most of the power, if you see from between 5 and 10, right? It doesn't matter where you are building, whether it's Spain or all the high. So like today, like Hamid showed me this beautiful graph with a lot of intensity of solar, really dark brown color, okay? And in those areas, you get efficiencies of around 10 watts per meter square. So if you look at every solar farm is below 11.4 watts per meter square, and the US average is around 7.5 watts per meter square. And in Northern Europe, which was totally blank, okay, is 5 watts per meter square, okay? So the question is, okay, so these are the things, and how can we meet our needs, okay? So if you look at places like Germany and UK, okay, so their solar farms, like as I just showed you, 5 watts per meter square. And then if you look at all their energy need they use as a nation, okay, and then take that energy and then convert it to power and say per meter square of the land, because that's how we'll be getting the solar energy, right? So how many watts per meter square they are consuming, okay? So they are consuming 1.25 watts per meter square as a nation, okay? And the solar farms will generate 5 watts per. So if they wanted to meet all the energy with solar, they will have to cover close to 25% of their country. And could they cover 25% of their country with the solar farms? I will leave it to your imagination, okay? All right? So let's come to US, okay, where we are blessed with a great nation with a large area and so forth, okay? So if you do the calculations, US power requirement is roughly 0.4 watts per meter square, okay? So 4 to 6% of the country's land need to be covered, okay? And do we have that land to cover is the question, okay? And so let's examine, okay? So what we did was in my group, we just can't take primary energy and do it, right? Because we need to know what the end use, right? So with the PV, with the electrical energy, we'll meet the consumption. So what my student did was, she divided all the consumption into electricity generation, residential area, transportation area, industrial area. So we divided all the uses we have, and I will show you just one, just to give you a flavor of what she did. So she took like petroleum and energy, for example, and you have gasoline is being used to drive the cars. So you can take this gasoline, the efficiency of it, average efficiency in the US of automobiles is 14.8%. Then you know how much is real work, right, out of it. And then you do the same thing with the solar. You take a PV, you produce electricity, 4.7% transmission losses, so 95.3% efficiency, it comes to the automobiles, and those engines are 75% efficient after the motor efficiency, battery efficiencies, and so forth. And these two numbers should be the same, right? Because the end use is the same. So you can back calculate this way for each sector, how much is the electricity need to be produced. That's what she did. And then what we did was, we look at the land. So if you look at the land in US, there are certain classifications of land. Okay, so the urban area, which uses houses, roads, shops like Chicago and places like that, is 3.2% of the total land area. Okay, miscellaneous land areas like marshes, deserts, barren lands, and so forth is 3.6% in US. Agricultural is the largest part of the land area, which is not a surprise. As a human race, that's what is our primary thing has been since the dawn of human civilization. Okay, so close to 54, 55% of the land in US is agricultural land. Land area for special like national state parks. So I'm in Denver right now. I'm enjoying national parks every weekend with my wife, just for your thing. I think it's a wonderful thing to happen, okay, in this world. It's beautiful places, like, I tell you what, Midwest. Sorry, if you go to West, like, it's just Colorado, Utah, like, it's absolutely out of this world. You go to those places, you sit, you look out of it, you say, man, where are we, right? Okay, it's close to 9%, and we need to thank all those people who are responsible for this, okay, really do, okay? And then you come to forest use, there's 30%. So the catch is, where are you going to put your solar farms, right? Okay, and note that the urban is only 3.2, and I told you that the US land area is 4 to 6%, we need 4 to 6%. So again, okay, so what looks like a large land area could be a problem. And of course, we can't put solar cells in agricultural places, because if we did, they're causing shadows, and since they're causing shadows, okay, the 85% of the photosynthetic activity is lost, and you are totally done, okay, is the right word, okay? So the student, what she did was, she said, okay, but let's look at every state by itself. Okay, so we know how much power is consumed by every state, and we know what's the land area of that state, and we know what is the miscellaneous land area, and what's the urban land area, and can we meet the local need? So the local photons for local needs. Okay, so we talked about microgrids this morning, and that's what the concept is. Okay, so every concept. So what you do is you look at it, and what she did was, she said, so we did a lot of paper you read. They say that we cannot use more than 15% of the urban area for PV. Okay, the upper limit is 15, more likely between 5 to 10% of the urban area, because not all the rooftops have the right orientations. There are shadows and so forth and so forth. Okay, so 15%, and then she assumed that 50% of the miscellaneous land area is available. When you do that, if the PV park output, remember, US average is 7.5 watts per meter square, and if you took 7 watts per meter square, and now we're not comparing primary, we're comparing end use to end use, okay? And when you do that, what you find is 30 states need more than 15% urban and 50% are miscellaneous. That means those states, if the PV power output was 7 watts per meter square, they will not be able to meet their needs, okay? So that will be a challenge, okay? Locally, they will not be able to meet locally. And if the PV power output was 11 watts per meter square, then you find that 20 states will not be able to meet their needs. okay, if they decided to meet. Okay, so that's the challenge, right? See, what looked like plentiful in the beginning when I started my research suddenly now start caving on me, right? Okay, because indeed, if you were to make a full transition, we could face challenges. Okay, all right. So, should we give up at this point in time? The answer is absolutely not. That's why we are doing energy systems engineering. Okay, and the question is that situation could get worse, right? The population growth, economy growth, okay, and higher energy consumption, okay, more food demand, okay, and then what are we going to do? So there's a competition between food and energy in the sense that I would like to install my PV farms on the agricultural land because it is 54%, right, of the total land. And yet the windmills are on the agricultural farms. So what should we do, okay? And the answer is, okay, go and find more answers. Okay, so what we did was we look at the solar spectrum, and the solar spectrum, of course, there's a visible part of the solar spectrum. There are IR and there are far IR part of the spectrum, and this is what plants need. Okay, plants need the visible, just like us. Our eyes are tuned for that, and so is the photosynthetic activity is also tuned for the same wavelength. Okay, so what we came up with a lot of solutions right now. Okay, and use this for food, use this for energy, and of course, if you want to do water purification, you can use the higher heat for water purification. And there are many possible solutions, by the way, even before I proceed. If we could sit here literally for the next 1 hour and talk about possible solutions to use PV on agriculture farm. Okay, I have students doing currently, 3 students, or rather 4, actually 5 graduate students doing research on this. Okay, so this is a big topic in itself. So I will just give you a glimpse of what could be done. Okay, basically you could, in an extreme case, you could build a concentrator, you could put a dichroic mirror. What it does, dichroic mirror does is lets the low wavelength photons go through, and everything else is reflected. You can put a solar cell, and so there's no shadow of the visible range. There's only IR shadow underneath, and you could grow stuff. Okay, and there are many ways of doing it. I'm just, in the interest of time, I think I'm running out of time. Bottom line is, once you decide to do it, that shadow which I showed you, okay, is just, you just put it up, but it all has to come from starting from ground zero, and that's what I was trying to emphasize to you. Energy systems engineering is very important. Going back, looking at photon spectral distribution and synthesizing new things. And once you do that, what you find is if PV power output was 7 watts per meter square, then some of the arrangements we have come could produce 4.4, and now 4 states will need more than 50% farmland, otherwise you can meet. There's 30 states, out of those 30 states, 36 could meet local need with local photons, okay? And same thing if it was 11 watts. Remember, there was 20 states which we had, but 17 could very easily meet their local energy. So this is a big news, right? This is a big change from building $1 trillion worth of power supply lines from the regions of the United States where there's a lot of sunshine to the regions where there's not. Now almost all the states can meet their local needs with local photons, and you can imagine at the county levels generating power and purifying and microgrids, which is what I loved what I was shown. I think having microgrids locally and meeting the needs and everything interacting outside and spanning outside, I think that's where the future will evolve. Okay, so what do we have? We have we just got an RT on this, on food, energy, water, purification, and we are building these things at Purdue, by the way. Okay. Unfortunately, the supplier who was going to, so we just got it this fall, and the contractor who was going to build just got bankrupt. Okay. So that's a big setback for us, because that means this summer we will not be able to do our experiments on the farmland, because now we are scrounging to get some other supplier to come and build this structure. So we are going to build this structure on agriculture. And we have agronomists who will grow corn, and we will monitor them and make sure that we can produce electricity and grow food at the same time without hurting the food production. So it's a real case. So this year I was so happy, even though I'm on sabbatical, I was happy that it was really done. But we just learned last week that the people who were going to, you talk about research, there's so many factors which are out of your control. I'm so disappointed. I literally, as a human being, I'm totally disappointed, because I was looking forward to this summer, having all these drones going and collecting data and telling me what's growing and so forth. I'm very, very disappointed. But anyway, I have no control on that, okay? And by the way, this is going bankrupt because of the laws and regulations which are being passed in Washington, D.C. So that's like something I have no control on. Okay, all right. So But harnessing, so what is the vision? What's the vision? Okay, the vision is take the solar energy, harness and transform. Biomass is a carbon source. Make hydrogen, which I did not talk to you about because of the lack of time. There's a big part of the research which goes in making hydrogen. You produce electricity, you get heat. You make your fertilizers, right? You make nitrogen from atmosphere, take energy, make hydrogen here, make a urea, so forth, make your chemicals from the carbon sources, resistance of water purification. In short, the vision which I began in 2004 on that ride, how would we live, how would we go and do, and here it is. Like we can now have all the spokes which we can connect and build the entire scale, okay? So this is, all right, so those are the mornings. So I think how much time do I have left? Like 10 minutes, is that okay? Okay, so what I will do is I will take you through part of the another journey. So that's the energy systems modeling I do in trying to, and that is done just to understand what are the important interactions and so forth. And as you saw from the presentation, one of the most important aspects about all this is creating electrons from sun, producing electricity, okay, is absolutely the driver of the whole thing. So as a chemical engineer, what am I going to do to produce electricity from sun, okay? So what I will do is I will talk to you guys about solar cells, my research on, so that's another thing I started after coming to Purdue. I had no research on solar when I came to Purdue. I had really zero, I had an empty lab with no beakers and nothing, and credit goes to my first 2 graduate students who really made it happen. Like, you know, I got some of the brightest kids planet Earth can provide, and I'm very fortunate for that, actually. And so my first graduate student, Chija Goa, like he came and he just what I'm about to show you, like, you know, he did, I would say, 50% of it single-handedly, actually. And so what is a solar cell? A solar cell, just for people who may not know in this audience, is a multi-layer device. It has many layers, okay? It has absorber, like as you can see from here. It has molybdenum polydiacylonide. This is copper indium gallium diselenide solar cell. Here's the absorber layer, is the calcium sulfide layer, is zinc oxide, the conduction layer, grids. So there are many layers. Basically, solar photons come, they absorb, create electron hole pairs under the electric field, internal electric field. They separate out, they flow in the external circuit. The circuit is complete, and we are done. Okay, so that's the device we need to prepare. And so we prepare like absorber layer, and the complete device is prepared in my lab, by the way. Like we start with glass and complete the whole thing. And why liquid processing? Because we decided to do liquid processing because it is deposition. We believe, I will just go here directly, because the liquid processing, because you can do it at atmospheric pressure. You can do it fast. It's roll to roll. Like, you know, you can spray your ink. You can make it. We grow large grains from nanoparticles. Then it goes on a roll. We can put all the layers. So you can produce. Remember I said earlier, it has to be a low cost. It has to be high efficiency. And if you want it to low cost, and coming from my industrial experience of chemical engineering, what we are looking for is something which you just print, and you just go, and you're just going through the whole system. So I was looking for something which I can hang my hat and do the research, and that's why we picked this. Okay, and truth be said, and my reaction engineering background almost forced me to do it, because then I can use my principles of reaction engineering. You know, A goes to B, goes to C, B goes to D. How they're interacting. So nanoparticles. So something where I could follow a little bit. You know, totally new field. You don't know anything, then you'll be lost. But you know, it allows you to do that. So we consider 2 solution-based approaches. Okay, so basically in one of the approach, we make nanoparticles of compound semiconductors, mostly chalcogenides, okay? And then after we make ink, it's just no different. When we are done, this ink is no different than the ink which some of us might have used on our fountain pens, okay? And then we deposit that by spray coating or by Dr. Blade coating or whatever have you. And then what we get is a cross-section you see here. So if you break it, look at the cross-section. They're all nanoparticles. They're packed together. And then we selenize it and make the large grains, because we need a micron-sized grains. So we make micron-sized grains. And then finish the device. Okay? So this is the nanoparticle method. Or recently, like 3 years, 4 years ago, we discovered in our lab that we can dissolve things like coppers and the indiums and galliums and zincs and tins, like in amine thiol mixture by just serendipity, like in the lab. And one of the guys' friend was very smart. His name was Bryce Walker. He just happened to observe one day that he happened to have thiol and amine, like we are using in different. It happened to be together, and thing just dissolved away. He said, "What happened here?" And then that led to this part of the research. So graduate students are very critical in the lab, by the way. You know, I sit in my office. I have no clue that if you mix the 2 things to dissolve. He came to my office. He said, "You know what, Professor, what happened today? My earlier step was not totally completely washed, and when I mixed, the thing disappeared." I said, "That's interesting." And before you know, a whole new research evolved out of it. Okay, so we can dissolve and we can make molecular precursors. We can make inks. Okay, we can coat. So we are pursuing now both methods of making. So we found a. So in my lab, so what we started, like copper indium gallium diselenide solar cells. So we have a 15% efficient solar cell in the lab now. So we can make 13% on a very regular basis, but 15% is the champion device. And we are marching. And that's what my sabbatical is right now. So I want to take it to 20%, and this whole sabbatical is being focused on what to do now to take it to 20%. Okay, so that's what the whole thing is. So it's a totally solution process. We can go and do it. Okay? But how to make it form? But you see, copper, indium, gallium. Indium is like tough, like it's used in TV and everything, and has a huge demand. So how to do it with earth-abundant materials? Okay, so to do it with earth-abundant materials, early on in my group, we started to look at copper, zinc, tin sulfide. So the structure is same as copper, indium, gallium diselenide, except what you find now is that indium and gallium, which are like here, have been replaced by zinc and tin. So if you look at two atoms, one atom of zinc, one atom of tin, you have +6, and 2 atoms of indium or gallium will give you +6. So you can replace 2 atoms of indium and gallium with 1 atom of zinc and 1 atom of tin. Okay, you have the same structure. So that was good. So we went ahead, we prepared those because now copper, zinc, tin, and are very earth abundant, like they're everywhere. So if you're making on a large scale, because when you're making photovoltaics, think of it, right? We have to make in a really scale, unprecedented scale, like So you need to have these materials available to be able to do that. Okay, so that's why this research was started. So we made the films. These are micron-sized grains. Okay, which you are seeing again. You have a film, you break it, and you look at in SEM, is scanning electron microscope. You look at the cross section. This is the top view. We can make the particles. We can make the solar cells. And these are efficiencies are 9.3%. So we got these high efficiencies very early on, like 2010 and so forth. But what you notice is after 2010, we start making progress. Okay, so no matter what we did for till 2015, the efficiencies were always like 2013. It was always the same efficiencies. And then we said, okay, wait a minute, something is not right. Okay, so we began to do a lot of analysis, and what we find is that no matter what we did, and so we did. I will not go through. We have published papers on this in Applied Physics Letters and Journal of Applied Physics. Like we did a lot of, and it has a lot of. Basically, it has bent tails and it has defect chemistries, and there was no way we were going to improve this material. Okay, so it became very clear to us that. So what are we going to do that? So if you wanted to improve, we had to tune the material properties, because those bent tails and all are not good. So we had to come up with a new alternative. Right. So what we did was we started tuning the defect physics. So defect physics related with tin, we started to substitute some tin with germanium to fix that. Because what happens is, if you look at copper, just to give you in one line, copper, zinc, tin, right? Those ions like copper plus, zinc double plus, tin 4 plus, they're all similar size. Since they're very similar size, they don't want to go at where you want to go. So if you look at the structure, crystal structure, they are where copper wants to go, zinc goes, and where zinc wants to go, tin goes. So there's a whole mixing there. And worse is that tin can exist as +2, it can exist as +4. If you look at copper, it can exist as +1, it can exist as +2. So all this is bad news, okay, for this thing, okay, and that's one of the reasons. So we decided to plug all that with this. We did that with copper, with silver, and we saw some improvements, okay, with germanium. We improved a little bit, but really not much, okay. And with silver, we are still working on the lab with silver. And as you incorporate silver from 0% to 5% copper replaced with silver, 50% copper replaced with silver. With silver, you find that you can make large grains, okay, which is very good news. And if you look at the time-resolved photoluminescence, what you find is as you substitute more and more silver, your lifetime improves of the minority carrier, which is also very good news, because if the lifetime is improving of the electrons, that means you have more time to collect it. So the likelihood of having a more efficient device is good. However, since we put silver, we have moved the band edge locations, and we have to find new matching N-type materials. So everything comes with the challenges. We are working on it. Hopefully in a year or two, I will have a better story to tell. But for the time being, the efficiencies have remained low, okay, and we are looking for the other semiconducting materials. And I put this slide because of Hang Wang. So after I realized that you were on my list, you were here, I said, okay, all right, I'll put some slides. So we made these materials like copper arsenic sulfides, also earth-abundant materials, okay, totally done for him, okay, by the way. You guys don't have to pay attention to it, okay? So this is, I just wanted to show him that we did try to make for photovoltaics a whole new class of materials, and they happen to have the right band gap also. So if you look at the copper, and this is the material which is selenide, which is what you published actually, and for thermoelectrics. But so we can form selenides also. So we have done this for selenides also, and for this, and you can see that we can tune the band gap, which is good news for you can make a top layer photovoltaic, you can make a bottom layer, and so forth and so forth. And we can grow we are trying to grow the films. You're asking me, like, here's the nanopart. We're trying to grow the films. Okay. All right, so search continues. In my sabbatical now, hopefully when I go back, I'm bothering my graduate students all the time. Every second day I'm calling them, hey, let's do this. I just learned this, or I just learned that, and this is the equipment. This is just like but it is exciting. Okay, so time is up. Let me just tell you, to sum it up, the challenges and opportunities, which is what we talked about. So what are the challenges? What I tell you? Energy systems engineering I find very, very useful. Okay, I quite often find myself asking wrong questions, okay, and finding wrong answers. How big is my system? How to analyze it? How to come up with the right solutions is always a challenge. Okay, we must avoid this. And unintended consequences quite often, like, happens when we are finding. And so we need to find newer and newer technical solutions, and never take no for an answer. So one of the things is when we are doing this, quite often, like as I showed you about should we be using agricultural land area for PV? The initial answer is no, because if you look at all the papers which have been published, they say, no way, just go away. No, let's go back and look at the solar spectrum, ask the right questions, and go and do it. Discovering synergistic solutions is a very challenge, okay, because it's one thing to say I'm going to use hydrogen, and I'm going to use electricity, and I'm going to use biomass, and I'm going to make, it's one thing to say, and to come up with the right process engineering perspective, which you can go and build, is a totally different story, okay? So there's and it's a multi-scale nature of problem, like from photons and from nanoscales of molecules and nanoparticles to micron-sized grains to building structures which will be in the farm, like, really meter by meter, 4 meters high. You're growing, so it's a whole scale which you need to, and that's what same thing as Hamid was telling us last night. Droplets of the rain falling on the wind turbines, collecting, going from Lagrangian to Euler scales and 25 parallel computers and doing 2 seconds. It's very impressive story. These engineering problems are very multi-scale, and there's a big challenges to these. Okay, and so the other lesson to graduate students, especially to graduate students, what I wanted to tell, I came to Purdue as a very traditional chemical engineer who even did not know what a Fermi level is, let alone going and building a solar cell, right? Okay. So you have to go and learn all that, okay? Build on your core structure. So when I built the solar cells, my only strength was I knew the reaction engineering part, okay? How to do the reactions. But the rest had to be learned. Okay, so read, learn, okay? So build on your core strength, and that's the challenge, okay? And one has to think differently, which is and in academic institutions, it is much easier to think differently because of the graduate students, okay? I always have graduate students who come and throw at me a curveball, and I just sit there and look at them and say, wow, okay? And so a lot of creative minds, okay, young people who are there who help you in this journey. So that's also a very important aspect. Opportunities, of course, all the challenges are opportunities, okay? Thank God there are a lot of challenges, okay? If there were not challenges, the world would be a dull place, right? So it's a good thing, okay? Increase the application dimensions, okay? Local photons for local needs. I have a vision, and I think today, that's why I think coming to IIT was very fruitful for me, because I got a first glimpse of microgrids and how IIT campus is geared towards that, how the local things. And I think the way I picture it is, okay, so I used to think of county to county and county interacting and the states interacting, but I think from a campus and proceeding to a city like Chicago and going is great. Distributed versus central system, new chemistry, new materials, processes, applications. This is so exciting. These are all, in my mind, are perfect. Best of all, I'm learning new skills all the time, okay? Like for the last 3 months, I've been learning new tricks, and that's phenomenal. Like, you're always on a journey to learn, okay? And there's no substitute for that, really none, okay? I'm always reading some papers, someone is showing me something, just phenomenal, okay? And in all that, why do we do that? Okay, because as I started the journey, in 100 years, maybe perhaps the human civilization can live off the solar photons, right? You want to make an impact, you want to change it. It is a sustainable world which can go on its own, okay? And it is a vibrant and exciting opportunities for engineers and scientists, okay? I think this is as good as it can get, in my opinion. Like, I think this is the best of the times to live, okay? Because we have to make this transition, and this is what makes it so exciting, actually. And with that, like, I would like to acknowledge them like graduate students, because I get the opportunity to come and present, but I tell you what, like, they are the ones who really make it happen, okay? And I'm fortunate to have them do, and they can't come here, but I come and I present their work. So it is absolutely wonderful to have graduate students. And of course, the funding agencies which fund my research, because all of us who are in academia, we know that no money, no research. So it's very important, okay? And with that, thanks to all of you for coming and listening to me. So I'm really ashamed of myself because I have not done that calculation being born in India and having grown, right? You would think that I would be the first one to do that calculation. But one of these days I will do that. Okay, right now these things we are doing it. But your answer is, I would say with 90% confidence that is probably correct, because even with 11 watts per meter square with the population density, like, it's certainly, yeah, absolutely. And I think what happens is, even if you go to a country like India, like when I was growing up, everything is agriculture, okay? You drive from town A to town B, and you look out of your car or train, whatever you're taking, the farms and on east side. So the question is, like, wind turbines you can put at places where there's wind, but wind is not everywhere. So if you really wanted local, so how do you build these things, right? So they coexist. I think as a human civilization, what I think personally is that the day we learn how to have food and energy coexist together, this is perfect for us, and that's what will happen.
So I think a very important message you're giving us is the method of localization and distribution. Mm-hmm. We used to think in terms of huge projects and things like that, but that is one way of solving things. The other one is to use things where they are.
Yes, that's correct.
And one of the questions I want to ask about localization is, what can you tell us about advances in light storage?
In storage, that's very true. That's a tough one.
So where you don't go the route of electricity or whatever, just store it and use it. And I know it's a much more challenging thing. There are a little bit of research coming out, but what is the most recent on that?
I really don't have much to say, but it's certainly the most challenging aspect, which I totally did not discuss at all. So what we have done is we did some modeling on storing energy on the large scales, but they're more like I don't know whether we can use it on a local scale or not, but it was more like using solar thermal, okay, and using solar thermal to co-produce electricity and hydrogen, okay. So people think of solar thermal as making just electricity, or solar thermal just making hydrogen, but it turns out that if you make both, it's a very efficient process, okay. And you could produce both, and you can produce hydrogen directly at a high pressure, okay, and store it, okay. And then when the sun is not there, use that as to electricity. And you don't have to use solid oxide fuel cell for that, like in the sense that you could use turbines, which you would use with the solar thermal, steam turbines. You can still use the same turbines with using hydrogen as a fuel, because you could burn hydrogen in water, in gaseous water itself, and you can get very efficient processes. But that's a large scale storage, okay, because that's not a small scale storage. So I don't know. I think that's a holy grail. If the day we find something which can store, batteries are it's low level. Batteries are the only choice as of today. But the question is what it could be. Certainly, by no means I wanted to ignore. So we have done a lot of energy systems engineering work on storage. Okay, using even carbon, methane, dimethyl ether, ethanol, methanol. Okay, so we have come up with the loops of storing energy as liquid methane and then converting it into liquid CO2 and storing it. And so there's a whole things we have, but none of those are still, in my opinion, very attractive in terms of small scale.
My question is actually related to the one Dr. Timur just asked. Almost 30 or 40 years ago, probably in the same auditorium, I listened to a distinguished lecture about solar energy, and I left with an impression that storage was the holy grail, which is what you just said. I want to see if I got your message correctly today. Going through the system analysis, the global system analysis that you discussed, I actually got a different message. You're basically telling us, at least for the US and India's and other countries, maybe another challenge, is the hybrid agricultural solar collection entities are, in your opinion, the holy grail?
Is important, yeah. And I think ultimately it will, at some point in time, it will, in the beginning it won't be because you have to use up that 15% of urban and miscellaneous. But once that crosses, that indeed that would be the case. But I was giving even a bigger message than that. Like whatever use we are looking at, we need to look at, make sure the system we are looking is the right system, the boundaries we are drawing in our analysis, okay? Like for example, when I said, okay, you want to make transportation from, so if you're just making a liquid fuel, so we have the message I was trying to give, there's a much bigger system, and we need to make sure that all those interactions, and food and energy happens to be one of those interactions, okay?
Yeah, but that's
okay.
the global one.
Yes.
The local ones, you can think of vehicle,
yes.
train, or car.
Yeah.
Solar collectors and battery storage.
Yeah, that's correct.
With
That's
20 years more research than we have now, and it will be self-sufficient.
yeah, could be.
You don't have to do
Yeah,
anything.
that's correct. But on the other hand, but you may not have the land to put all those PV collector for all the cars and all. So that's the that's part of the message.
To me, at least for the
Sure.
U.S. with a large mass of land, it appeared
Yeah.
to me from looking at your analysis.
And that's a surprising result, actually, to some extent, okay? Because to me, it was surprising, actually. Okay.
Hi.
Yes.
That was a wonderful, wonderful seminar. I have a question about your experimental section, like
Okay.
the later part. It seemed to me that a lot of your conclusions are based on experiments, and if the efficiency, you hit a plateau, you have to try a new material. I was wondering if there are any principles that could be applied to make this process faster. So without actually going through 3-4 years of experiments and figuring out which is pretty obvious now. I don't know if there's any.
Yeah, so that's a good point. Actually, it's some of you who did not hear the question, like, do you have to do experiment for 3-4 years, 5 years, which is what I described, and then come to the conclusion, oops, I just wasted my 5 years. Could we do that in a week or a month or something like that, right? And do some fast computational / fast combinatorial / some of those things. And those are all certainly possibilities. And I'm certainly a victim of what I don't know, okay? And so the way I would say it is, so now when we are working with the other materials now, so we're asking all those questions now, okay? And analyzing all those things now rather than wait for, all those class of materials I just described to you, we're already measuring the lifetimes. We're already measuring the mobilities. We're already measuring the Urbach tail energies. We're already measuring, so I'm not going to spend another year with this unless until I meet those, so I know now, right? Okay. And can combinatorial methods help? Absolutely, with some intelligence built in trying and that's what the material genomics part of the NSF is. And I just attended their meeting last week, actually remotely, because I could not, I'm not traveling right now. But the point is that you're absolutely right. There is a need to drive conclusions faster. The only thing which I do not know in this, and I must confess, so once I know the material property, another part is what could be the structure of the solar cell? Does it have to be the same structure I showed you? Okay, what are the possible structures which could overcome the material property? Now that's where the human ingenuity comes into the picture. And that part I'm just beginning to explore now. Okay, so if you give me a material property, rather than thinking of conventional cells all the time, what are the other possibilities which may exist, right? Okay, and so So let's see what happens. And maybe that can, once we learn enough, maybe that can be built into the some kind of artificial intelligence system, which can. Point well taken. Point. You can't afford to spend. It's a point. Yeah. Yes.
So really nice talk. So one of the issues with renewables is the cost of energy generation. I mean, with natural gas, fossil fuels at about 3 to 5 cents per kilowatt hour, without subsidies, these renewables face a challenge in terms of widespread adoption. And with your schemes of having heliostats that are transparent to UV radiation and reflect infrared, these costs are likely to be even higher than what they exist. So could you comment on that issue?
Okay, so the two aspects of your question. First is forget about what I showed, just on the photovoltaics, how will they compete with natural gas? The first part of the question. And I would say that in some parts of the world that is already happening, okay, because not everyone is blessed with cheap natural gas as the United States is. So for example, like the countries like India and others which were mentioned earlier, like energy prices are much higher, and the photovoltaic prices, the solar cell prices have come down tremendously actually, and to the extent that now they can make anywhere, I would say 7 cents to 10 cents a kilowatt hour. So they are competing very well in large number of markets. Even in US, like I think First Solar is building these things, big farms, which are supplying electricity at a low cost. So I think the cost is coming down and has come down substantially, much more than in my last 13 years of research. They have gone by a factor of almost 10, like not actually $3.50 now, they're more like 50 cents. So they continue to climb down, and they will continue to go down. So I think the competition is fairly good now. But storage is still Achilles' heel. Okay. And regarding the solar farms which I presented, I just showed you one of the structures. Okay. And they're much cheaper structures which could be built. Okay. Which is so one of my colleagues, he's Peter Bermel, he's an electrical engineer. We're doing a lot of photonics, like light shading and all those modeling right now. And the early results are very encouraging. We can build systems now which are order of magnitude simpler than what I'm showing you right now. Okay. As I said, that could be a 1-hour conversation on its own. And there are dozens of possible structures you can build, and some are trivial compared to what is being done right now. Okay. So I don't think we will have to even go to using diachroic mirrors and splitting solar spectrum. I think we can get away without it. Okay. And that's why we want to do all this, build it on the farm and do experiments and prove that indeed this can be done. Okay. So your point is well taken. I think NSF has been very kind to give us the money to go and NRT to go and prove it. So I'm pretty excited about it right now. So
I would like to know your opinion about the photonic type of crystals. They actually, it's like a photomultipliers. They're able actually to collect some kind of wavelength to increase the amplitude, and this way you can produce more energy. And the second, my question is about the storage of energy. Generally, the people right now use capacitor, a huge capacitor. This is more simple way from solar energy to transfer and to store in capacitor.
Capacitors.
What is your point?
So I really like, I don't have any specific opinion on either of those two. I think it is part of a continuing research and see what happens, because capacitors, like given a large burst of energies, they can store and give. So they have an application for their places. And
How they use this kind of capacitor?
yeah.
Solar.
Yeah. So there's a room for that, but
It's easy
so.
to store a huge amount of energy and after that to release for a short time.
For a short time, that's correct. And so it's one of the options on the table, I think. So certainly. And regarding the other, from the plant perspective, if at least in this part of the world where we live right now, farmland is ineffective for more than half of the year. Okay, so for the farmers to have this thing and get an additional source of income could be very attractive if we are successful. So there's another aspect of it which is a possibility.
Are there advanced materials like graphene that offer potential, or are there other materials that are currently offer a lot of promise to create a more efficient collection, distribution, storage system on a distributed level, you look at the picture behind you, half of that real estate is rooftop. So on a distributed basis, rooftops would seem to offer a lot of potential for collection.
So from my window, I can see the rooftop of the physics department. And one of my goals is, before I retire, to have that rooftop covered with photovoltaics. So your point is well taken. Regarding graphene, there are a lot of people who are doing graphene research right now, and they're using graphenes more in terms of collecting as a conductive layer and so forth. So, but that's not part of my research, but a lot of people are pursuing and looking into that. Okay.
So going ahead, over the past few years, there has been increasing talks about life cycle analysis and how the solar panels are going to be dismantled, like going in the future, 20, 30 years later. So when you choose your materials or in your scope of research, how far ahead do you think about life cycle analysis of solar panels or energy systems on the whole?
That's a good question, by the way. Like, life cycle analysis, of course, is a must, actually, because cradle to grave, we have to know, the materials we're using, what their fate is, whether they can be used or not. And do I spend a lot of time doing it? The answer is no, the truth be said. But some of my graduate students, they're inclined. So, for example, this material, which I showed you, like Cu3SS4, without even asking me, he went ahead and he built this prototype, this agitator, like autoclave. He put the material, put some acid, some base, stirred it. He's studying the toxicity effect, how many parts per million in the solution, which is a good thing to do, right? So the answer is, do we look? Yes, we do, but not to the degree it needs to be looked at, because sometimes if you do these things too early, then you don't know what solutions might evolve to protect it and to use it. So you don't want to just kill your ideas early on, because you might build a system later on which could recycle it, which could recover it, but you certainly don't want to make sure that while it is in use, it doesn't leach or it doesn't discard and things of that nature. Of course, ideal material will be the one which is just there and nothing happens to it, right? No damage.
Last question.
Your research is very promising, but clearly it'll take a while to commercialize it and make it economically feasible to utilize it. What are the public policy things that need to be done right now before, very cheap solar power becomes available?
So I think the public policy, the only thing I would say from my angle is the U.S. government has been the greatest benefactor, has been the greatest patron of doing research. So when I look at the history of human civilization, if I was born 400 years ago, for example, right, and if I wanted to do research, what is the likelihood of me born as a common human being and being able to do research? Zero. Yeah. The only way I could do research in that era was either I was born in a rich family, or I found a king or some wealthy human being to be my patron and give me money to do. On the other hand, the century we live in, I think U.S. government is absolutely phenomenal. The NSF, the DOEs, I think very fortunate to be in this part of the century, and they are the patrons. Okay, and I think from the policy perspective, if they keep clear what we are evolving and they keep funding the correct research, okay, rather than saying, we will never meet the cost. Okay, this is so I write proposals, the reviewers will say, this guy is just dreaming, this will never meet the cost. And I feel like sitting and saying, come on, give me a break, right? If it was cost, then industry guy would be doing it, right? Okay, so asking a question about cost to the researchers who are dreaming and developing solutions, I think, is a wrong policy. Okay, you should ask for a cost when you're building it. Okay, if I'm in industry and I'm building it, asking cost is the number one thing. Okay, we must. I was in industry for 25. That's all I did. Is it low cost? Is it low cost? Is it low cost? Okay, and if I did not do that, that would be a wrong thing, wrong service to my organization. But today, that's not the case. So I think, as a policy-wise, I think as long as the policymakers are right and they're funding the right individuals across the country to do the right research, I think as a nation, we will develop solutions which will eventually be low cost. Okay, and we will be able to implement it. I think that's how I believe. So that's what I would say.